Hey everybody, welcome to part 2 of the time value of money intro to finance lesson. In part 1, we kind of introed it. We talked about lump sums, how to find basic present values, basic future values. Now we're going to take it a step further. So this lesson is really all about annuities, perpetuities. Before we get started, if you are enjoying these lessons, please hit that subscribe button so you can get notified when I post more, and it helps me with the algorithm. So I would appreciate it. All right, so let's get started. Now, today's, like I said, all about annuities and perpetuities. We'll talk about what that means in just a second. Before we get into that, we need to do a deep dive on interest rates, effective interest rates. So what is an effective interest rate? Well, an effective interest rate versus, say, a nominal interest rate is an interest rate that actually takes into account compounding. See, a nominal interest rate, which by the way has many names, it could be called an APR most commonly, which stands for annual percentage rate. It could be called a QR for quoted rate, stated rate. These are the interest rates that the lenders or the banks will kind of state or say, but they're not the true interest rates because they don't take into account compounding. They're just nominal rates. For example, 10% compounded monthly or 10% compounded annually or semi-annually. Now, they're all 10%. You see, I stated 10%. But we learned in the previous lesson that that is not the same thing, right? Compounding once per year is not the same thing as compounding 2 times or 3 times or 4 times per year. And so the APR, or the nominal rate, simply doesn't take into account compounding, and therefore it should never be used as your discount rate. Whether you call it K or R, that's not your K or your R. It is your APR. Okay, we'll deal with that in a moment. So the effective frequency, the effective interest rate is the interest rate that actually is adjusted for the compounding frequency. And another key difference between them is that the APR, or the nominal rate, is always expressed annually. It's always an annual rate, APR, annual percentage rate. But the effective rate can have any time frame. You can have an effective monthly rate, an effective daily rate, an effective weekly rate, right? So you can adjust it for that. And we'll get into when to know which one you need. For now, understand that this is called an effective periodic rate because it can take any time frame. The effective frequency is based on really two things, but three things. The compounding frequency, which I'm going to use the symbol M as I did in the first lesson. The payment or the period frequency, which I'm going to call F. Basically what this one is, we talked about compounding in the previous lesson, but the period frequency is, the frequency of the payments. And when we were doing lump sums, we didn't really make a distinction between M and F because there is no distinction. When you don't have a payment, there's no F, really. But when you start to have recurring payments, which we'll have in this lesson, F starts to matter, the frequency of the payment, and it is not necessarily going to be the same as M. You could have semi-annual compounding, but monthly payments, like in a typical Canadian mortgage. Right? Mortgages in Canada are paid monthly usually, but the interest on them is only compounded semi-annually. So you see a difference there between M and F. On the financial calculators, M is called CY for compounds per year, and F, the frequency, is called PY for payments per year. Okay, so when we're going to be using the financial calculator, we'll introduce those things. Now, the formulas, you have them underneath. The first one is to find your effective annual rate, specifically annual, with periodic compounding. So you see the formula for it. This is probably the one you'll use the most. It's 1 plus the APR divided by the compounding frequency to the power of the compounding frequency minus 1. Okay, this is for an annual rate. Below, you've got another annual rate, but this time with continuous compounding. This is probably the one you'll use the least. Okay, e to the power APR minus 1. It's still an effective annual rate, but very specific to continuous compounding. The third one, also very common, is the periodic rate. So this is the one that you would use if you were looking for a monthly rate or a daily rate or a weekly rate or a semi-annual rate and so on. And so the formula is 1 plus APR over M, like the EAR above, but the exponent is where the difference is. We use M over F, the compounding over the payment frequency minus 1. And lastly, this is the effective to effective formula. So the first three here, those are used when you're trying to convert an APR into an effective rate. But the last one is when you already have an effective rate, but you're trying to convert it to a different one. So you can see K new is the interest rate I'm trying to find, is found by taking 1 plus K old, the effective rate that I have, old F over new F. Now, that might seem weird for now, but you'll see in a moment when we solve the exercises, this is a pretty good way of remembering it. Okay, so these are the key formulas for effective rates. And why this matters so much, once we get into solving annuities, perpetuities, or even growing annuities and growing perpetuities, the first step is always going to be to make sure you have your effective rate and that you have the correct effective rate. So this usually becomes like a step in a question. Okay, so let's do a few exercises just to get to know those formulas. So what is the effective monthly rate? Okay, so right off the bat, I'm looking for a monthly rate, which means the F that I want to have is 12. Okay, F is the effective frequency. It is not the compounding frequency. In this case, the compounding frequency is 365. You see, you're told there that you're compounding 365. So when you're trying to find an effective periodic rate, and remember, that means anything that is not annual. In fact, guys, you can even use this formula for annual rates. Basically, this is your default formula. The only thing you cannot use this for is if you have continuous compounding, really. So I'm going to start by, I'm just going to use the formula. So 1 plus the APR, which is in this case 12%, over M, my compounding, so 365, to the power of 365 over 12 minus 1. Okay, so, oops, so 1 plus 0.0, no, 0.12 divided by 365 to the power of 365 over 12 minus 1. So I get 0.01004, which if you multiply that by 100 is 1.004%. And this is per month. This is a monthly rate. So you see 12% compounded daily is equivalent or effectively 1.004% per month. Let's do another one. What is the effective semi-annual rate? Okay, so I want an F of 2, and my M, my compounding, is every 2 years. Now, that might seem weird, but your frequency, whether it's F or M, can have any time interval. We're used to seeing time intervals that are less than a year, like monthly or daily or weekly, but they can be longer than a year. In this case, what you do is you make a fraction. So every 2 years is 1 over 2. You're basically compounding half a time per year, right? If you're compounding once every 2 years, that's equivalent to half per year, okay? So if it was every 3 years, it'd be 1 over 3. If it was every 5 years, it'd be 1 over 5. And then you're going to use the same formula as question 1. So 1 plus your APR over M. M is basically 0.5. So 0.5 to the power M over F minus 1. So that's 0.033. Depending how many decimals you want to keep, it would be 3. Again, if you multiply that by 100, it's basically 3.33% per, and this is semi-annual, per half year, right? For every 6 months. Great. So you see, it's not actually difficult, right? If you know your formulas and you know what to look for and you know how to read your questions, this step is usually, shouldn't be hard. Okay, let's try another one. The effective, okay, 3-year rate. Oh, okay, so that means I want a frequency of 1 over 3, a 3-year rate. 10% is my APR, and I'm compounding monthly. So my M is 12. Same formula. So 1 plus 10% over M, being 12 in this case, 12 over 1/3. Now, when it's 1/3, I don't recommend just writing 0.33 because that's going to introduce a lot of rounding to it. So keep it as a fraction. So 1 plus 0.1 over 12 to the power 12 divided by 1/3. And on my calculator right now, what I'm doing is I'm putting that in a bracket, and I'm even putting this in its own bracket. So I have a lot of brackets here. I have exponent, bracket, 12 divided by bracket 1 over 3. All that minus 1. That works out to be 0.34818. Multiply that by 100 is 34.818% every 3 years. Okay. Now we've got continuous compounding. So we're going to use the other formula. This one here. So we're going to take e to the power 8% minus 1. Okay, this is the shortest formula there is in this part of the class. 0.08 minus 1 is 0.0833 or 8.33% per year. Remember, that one's the one you'll use the least, right? They really have to say continuous compounding. Here, you have an effective rate and you want to find a different one. So look, express an effective quarterly rate. So this is actually already a quarterly rate, right? We'll call this an effective quarterly rate as an effective monthly rate. So I'm asking you to convert an effective quarterly rate into an effective monthly rate. So let's grab the effective to effective formula and get to know it. Okay, so 1 plus K old. K old is the K you have, right? The rate I have is 2.2%, so 0.022. Old F. If I have a quarterly rate, my F is 4. That's the old F, right? That's the F I started with. And I'm trying to get to a monthly rate. So I want an F of 12. I have an F of 4. That's my old F. My new F is 12. So 4 over 12 minus 1. And for this, you're going to get 0.00728. Multiply that by 100 is 0.728% per month. Great. All right, let's keep rolling. So you see, that's a useful one. A lot of times your teachers won't show, well, some of your profs will show you that, but some will not, right? And so this is one that if you are not provided, I would definitely suggest memorizing, okay? Now, here's a different question. The subject is still interest rates, but it's more of a standalone interest rate question, whereas this here is just, you know, if the interest rate is a step in some larger question. Let's take a look at it. A bank is offering its clients a savings account with an APR of 8.5% compounded biweekly. Okay, so we know that this means biweekly. Biweekly means every 2 weeks. So M would be 26, right? 52 weeks per year divided by 2 is 26. It would like to offer another account that is equivalent to the first one. Now, when interest rates, or for interest rates to be equivalent, what that really means is that they have to have the same effective rate. That's the key here. They're basically saying, we want to offer some new account, but we want it to have the same effective rate, but with monthly compounding. What should the bank quote? So our final answer is an APR. Remember, a quoted rate is an APR. Okay, so let's see here. I know they have to have the same effective rate. So I'm going to take my effective annual rate formula, right? This one here. And you guys can pause the video and try and do it yourselves, right? I'm about to spoil the surprise. So if you want to try it, give yourself a chance. But basically what I'm going to do here is I'll take the rate that I have, 0.085, over M. The M is 26 to the M minus 1. Okay, and this will give me my effective annual rate. Well, I want the other account to be equal to that. So this is what I'm doing here. I'm using the same formula, but I'm setting my APR as an unknown because that's what I'm solving for. I'm going to set my M to 12 and solve it. You see, I've set the two effective annual rates equal to one another, and I'm going to solve for the unknown. Now to do this, I'll start by punching the left-hand side into my calculator. So 0.085 over 26 to the 26 minus 1. I get 0.088556. And now I'll just keep solving this algebraically. So I'll send the 1 over. So plus 1. So now I have 1.08856 and so on. I'm trying to keep all my decimal places on my calculator, right? To avoid rounding too much too early. Now we're here. To get rid of that 12, we can do a 12th root, or we can just do this to the power 1 over 12. That'll cancel out that 12. So I'm going to do this to the power 1 over 12. Okay, great. Now on my screen, I've got 1.007096 and so on. Again, not rounding too much. So I'll bring the 1 over, so minus 1. And then last step, you can multiply your 12 times 12. And the APR, without any rounding, is 0.08516 times 100 is 8.516%. So the new account would have to quote customers 8.516% with monthly compounding for it to be equivalent to 8.5% with semi-annual, or no, sorry, with bi-weekly compounding. Okay, great. So now we can get into the real part of this lesson, and that is the annuities and perpetuities, right? So what we just dealt with, very important, super important, but typically just a step in a question. So let's get into this. In the previous class, we talked about lump sums and how those are just single values at specific points in time. Well, annuities and perpetuities, okay, the two are basically exactly the same except for one minor difference, are recurring cash flows that have these characteristics, okay? Equal payments. Every cash flow is the same. Equal time between payments. So, a payment every month, a payment every year. A constant discount rate. So the K doesn't really change period over period. And for annuities, there are a finite number of payments. It doesn't go on forever. And that's going to be the difference between this one and a perpetuity, which will go on forever. Now, as far as annuities go, they can be ordinary or they can be due. This just means that for ordinary annuities, payments take place at the end of the period, which is the standard, right? Most cases are ordinary. And annuity due is when the payment takes place at the beginning of a period, like when you're paying your rent, okay? This would be specified in the question. And what's going to be really important for that, we'll talk about that in a second, is understanding really that all that changes is the timing of the payment. Whereas the present value and the future values, those are kind of stationary. And what I mean by that is, the present value of an annuity is always at the beginning of the first year. Whether it's ordinary or due, the present value is at the beginning of the first year. Or the first period, right? If we want to be a little bit less, beginning of the first period would be a better way to think about it, because a period doesn't have to be a year. It could be anything, okay? And the future value is at the end of the last. Again, I'm going to change that word to period, because a period could be anything. It could be a year, a month, a day, whatever. Here are the formulas that you need. Okay, there are many. The financial calculator can do almost all of these. It just cannot solve perpetuities. Now, a perpetuity is basically the same thing as an annuity. Has all the same characteristics, except for this one. Okay, a perpetuity goes on forever. Everything about it is the same, except that it goes on forever. Okay. Before we do the exercises, I want to make sure we're really understanding ordinary versus due. So like I said before, ordinary cash flows are cash flows where the payments take place at the end of the period. So what that would look like on a timeline, let's draw this 5-year $200 ordinary annuity. It means that at the end of each year, okay, these are the 5 years. And remember what we had said in the previous lesson. When you're looking at a timeline, this is the beginning of year 1, whereas this is the end of year 1, but it's also the beginning of year 2. That's important, right? Because sometimes you'll read a question and they'll say, the first payment is going to take place at the beginning of year 2. Okay, that's just another way of saying the end of year 1. There's really no difference. Okay? And so on, and so on, and so on, and so on. So if the payments are at the end of the period because it's ordinary, it means that the first payment would be at the end of year 1, then at the end of year 2, the end of year 3, the end of year 4, and the end of year 5. The present value is at the beginning of the first period. So here it would be right there, the beginning of the first period. The first period is the same period where the payment took place. The difference is the payment was at the end and the present value is at the beginning. The future value is at the end of the last period. So you see, for an ordinary annuity, the future value is at the same time as that last payment because they both take place at the end of the period. But you see, the present value we say is one period before because the present value is at the beginning and the payment is at the end. Now, for an annuity or a perpetuity-due, the difference is not in the placement of the present and future value, but rather the placement of the payments. So if you were to, write your 5 years again, it's a $200 annuity due, the payments would be at the beginning. You see, that is the beginning of year 1, the beginning of year 2, the beginning of year 3, the beginning of year 4, and the beginning of year 5. Take a look at that. Compare. Both of them were technically in the same year or in the same period. It's just that for the ordinary, they were at the end, and for the due, they're at the beginning. But the present and future value are in the same place. The present value of an annuity due is still at the beginning of the first period, and the future value is still at the end of the last period. It just looks different. Because in this case, the first payment and the present value take place at this, are basically at the same point in time. Whereas the future value is one period after the last payment. Because the payment was at the beginning, and this is the beginning of year 5, and this is the end of year 5. This is an important concept. We often lose sight of this, and a lot of times it doesn't end up mattering. But if you're faced with a conceptual question or a really, sneaky technical question where this starts to matter, you always want to know where on the timeline are you. Like when you find the present value, using one of the formulas that we're seeing today, you have to understand where that present value is in time. It isn't always going to be at time 0. And once we start to see the more complicated questions, you start to understand that a present value could really be at any point in time. More on that later. Okay. So let's get into our first exercise. Now for this, I'm going to do it twice. Once using the formula, once using the financial calculator. It's up to you to decide which way you want to do it. So for the first question, what is the present value of an annuity that pays $500 per month for 5 years? Now you see here, we didn't specify when, beginning or end. You should assume end, right? That's the default. So they're basically saying that you've got, and let me go and grab my formula. I'm looking for the present value of an ordinary annuity. So the payment is 500. 1 minus 1 plus your K. Now you see K is the effective rate. Except this is not an effective rate. We learned in the previous lesson that when I give you an interest rate followed by a compounding frequency, that this is an APR and this is your M. And so we need to figure out our K using what we learned at the beginning of this lesson. So I'm going to find my effective periodic rate, 1 plus the APR over M, which is 365, to the power of 365 over F. Now what is F? F is the frequency of your payments. So because your payments are every month, your F is 12. So we'll put that over 12 minus 1. Okay, it's up to you to find these and to notice that this is what you have to do in the question. Okay, so let's start with that. 1.365 to the power 365 over 12 minus 1. So so this is 0.00585. I'm going to keep 5 decimal places. To the power negative n. So what is n in this case? Remember what n is. N is years, so 5 years, times the frequency now. So the frequency is monthly. There's going to be 12 payments per year over 5 years is 60, so negative 60. Okay, if you want to make a note, n is just t, which is your years, times your f. All that divided by k, 0.00585. Okay, you punch that into your calculator, and you'll have your answer. Now, for those of you that are going to use the financial calculator, it's pretty much the same thing. We have a payment of 500. Your n is 60. Your interest rate is this number, but you got to multiply it by 100. So we're going to put 0.585 IY. Okay, so it's the same thing, but remember that you want to enter it as a percentage. I'm not going to use PY and CY, so we're going to keep those to 1, the default. You don't have to touch them. Now, when you're looking for the present value of an annuity on the financial calculator, you want to make the future value 0. Unless you're dealing with something like a bond or something a little bit more complex where there actually is a future value, generally there is no future value. And so you enter all those and you press compute. And whether you did it on your financial calculator on the right, or you're doing it using the formula on the left, the answer should be the same. Okay, so let's grab our calculators and we'll put that here. So 500 is your payment, 60 n, n, 0.585 IY, 0 future value, compute present value. So I get 25,000. Again, the negative sign doesn't mean anything right now. $238.97. Okay, great. So you see, it's just another formula to use. And essentially what this formula is doing is it's taking every one of those payments and finding the present value and adding them up. Because that's really what the present value of an annuity is, right? Remember this? Imagine you were to discount each one of these back. So you found the present value of the 200 as a lump sum. You found the present value of this one. You found the present value of this one, and this one, and then added them all up. That's what the formula is doing. It's discounting each one and then adding them up. Okay, now let's solve this question. It's a little bit different. What is the present value of a perpetuity? So again, it doesn't specify beginning or end, so we can assume that these payments are all going to take place at the end of each week, right? So on a timeline, it would be, $600, that's the end of week 1, the end of week 2, and that'll basically go on forever. The interest rate is 8% compounded weekly. Okay, so here you're going to see a special situation where you have a frequency of 52 because your payments are weekly. And your compounding is also 52. Now, what I'm about to show you is nice, it's easy, it's quick, but you can only ever use it in this situation where your frequencies are the same. So only when m equals f, okay, you can do this. Your k is just the APR divided by your m. Just like when we were doing lump sums. You can only do this, though, like I said, when m equals f. So don't start doing this all over the place. It's only in this very special case. So my APR here, my k, is 0.08 over 52. So 0.08 over 52. If you are going to round this, keep as many decimal places as you can. So this is 0.015. Let's keep 2 more, okay? There you go. That's your k. That's your weekly rate. And the present value is the payment over k. So if your payments are 600 and your k is what we just found, we get a present value of, now if you don't round at all, you should get 390,000. Now, whenever I get a number that seems a little bit off, I always like to do it twice. So 600 divided by that. Nope, I got the same thing, 390,000. That is the present value of this perpetuity. Now, it might seem weird, right? Like, how could something that goes on forever have a present value? For this, you have to understand that at some point, think of this as almost like an asymptote. At some point, the payments will start to be worth, almost nothing. A $600 payment is worth $600 today, sure. But $600, 60, 70 years from now, in present terms, is probably worth close to zero. So at some point, the present value just stops going up. In this case, the value is 390,000. Let's do another one. You will deposit $1,000 into your savings account each quarter for the next 10 years. How much will you have saved up at the end of the 10th year if your account earns 9% interest compounded monthly? Okay, so compounded monthly, that means our M is 12. You're depositing every quarter. Your payments are quarterly. That means your F is 4. So the first thing I'll do is find my K, my effective rate. So 1 plus the APR over M to the M over F minus 1. So 0.022669 is our quarterly rate. Great. Now, this is a future value because we're asking you how much will you have. So we want the future value of an ordinary annuity, which would be this formula right here. Again, we're going to do this twice, once with the financial calculator, once with the formula. The reason that I didn't do the previous question with a financial calculator is because you can't. Perpetuities have to be done using a formula. Okay, so here we are. The payment is 1,000. 1 plus the K, 0.022669. Now your N, it's 10 years times 4 because you're making quarterly payments, so 40. Minus 1 over 0.022669. Great. Now on the financial calculator, it's kind of the same idea. Your $1,000 is your PMT, that's the payment. We're going to multiply this by 100, so 2.2669 is the IY. 40 is your N. 0 is your present value. Okay, it's kind of like before. When you're looking for the future value, you want to set your present value to 0, and then you compute the future value. So let's punch this in. So again, whether you use your financial calculator or you use the formula, you should get the same answer, $64,023.14. Wonderful. Okay. Question number 4. We're doing a few of these, right, just to get really comfortable with this. You just won a lottery that promises to pay you $30,000 per month forever. Keyword there. So now we're dealing with a perpetuity again. The first payment being today. Ooh, that's important. On a timeline, that means you're getting your first payment right away, so $30,000 right now, and then every month after that, which means this is a perpetuity-due. The first payment is at the beginning of the first year. If someone is offered to buy the ticket from you, what is the minimum amount you should accept? Meaning, what is the present value? What is that ticket worth today? Your opportunity cost is 10% compounded monthly. So your M is 12. That's your compounding. And your F is also 12 because your payments are monthly. So there's that situation again where your K is just the APR over your M. So 10% divided by 12. Now, the formula for the present value of a perpetuity due is actually the same thing as the ordinary perpetuity. We're just going to add 1 year of compounding. And that's what that little piece at the end is, the 1 plus K. And you can see that on every due formula. So if it's an ordinary annuity or annuity due, or if it's an ordinary perpetuity or a perpetuity due, it's exactly the same thing. We just have to add 1 period of compounding, and that is, or 1 period of interest basically. And that's what that does. Okay, so let's grab this formula and go back here. So the payment is $30,000 over K. So K being 10% over 12. This is 0.0083 repeating. Times 1 plus K. Now for the repeating, I'm going to fill up my screen with threes. So 30,000 divided by 0.00833333. And fill it up as much as I can. Times 1.00833333 again, filling it up as much as I can. And I get a present value of $3,630,000 and 1.45. Now I bet if I didn't round this at all, if I had kept all my decimals to infinity, you'd probably get $3,630,000. If you're comfortable with fractions, you can just do this keeping your fractions, right? So 30,000 divided by bracket 0.1 over 12 times 1 plus 0.1 over 12. Let's try that. Exactly. 3,630,000 even. So it's really up to you. I, of course, would prefer this to get the exact answer on an exam. If you're keeping 4, 5, 6 decimal places, typically most teachers are fine with your answer, as long as you're showing your work, of course. Okay, so that is the present value. That's how much you should accept for your ticket. Anything less than that is not worth it. Here's another one. You're going to save $100 at the beginning of each week, for the next 35 years. Your goal is to save up enough money so that you can retire comfortably. Your account earns 0.1673% per week. Look at that. We gave you the interest rate per week, which means this is already your K. This is your effective weekly rate. No need to convert it, because the payments are already, the payments are weekly as well. So those two kind of fit together. How much will you have on the day you retire? Okay, I'm retiring in 35 years. I'm looking for the future value of an annuity due, once more due because we're saving at the beginning of each week. So let's go back to our formula sheet. Future value annuity due. You can also do this on the financial calculator. I'll show you guys how to do that. There's like an extra step to note. So the payment is 100. 1 plus the K, 0.001673. Okay, you see I'm converting it to a decimal. To do that, I took this number and divided it by 100. 0.001673. All that to the power n. So n would be 52 weeks per year times 35 years. So that is 1,820 payments minus 1 over the K, 0.001673. And because it's an annuity due, you need to multiply that by 1 plus the K, 0.001673. Okay, let's punch this in. Okay, so I ended up with $1,194,685.86. That's how much I'm going to have the day I retire 35 years from now. Okay, to do this on the financial calculator, There's really no difference in terms of like what you have to punch in, whether it's annuity due or ordinary annuity. There's just an extra step. So you still have a $100 payment. Your N is 1820. Your IY is 0.1673%. And the present value is 0. But your calculator has to know that the payments are at the beginning of the period. And so you need to turn on what's called BGN. BGN is a setting on your calculator. And as long as this is turned on, the calculator is solving everything as a due cash flow. So let me show you how to do that. On your calculator, if you press this sequence of buttons, okay, listen up. Second, BGN, which is the payment button. Second again, set, which is the enter button. You see the calculator will now say BGN, both large letters on the screen, but also at the top. Okay, so now if you clear that, you see the BGN stays. Now your calculator is set to BGN. So now everything you do will be due. 100 PMT, 1820 is my N, 0.1673 IY, 0 PV, compute FV. I get exactly the same answer. Okay? Now one thing that matters, if you are doing this, when you're done, turn it off. Turn off BGN. You don't want that to be on in the next question. How do you turn it off? The exact same 4 keys. Second, BGN, second, set. Or second payment, second, enter. Okay, great. So that's how much you're going to have on the day you retire. There's a continuation to this question. How much can you withdraw from your savings account 1 month after retiring? So now let's try and imagine this on a timeline. We already established that in 35 years you're going to retire, right? By putting away $100 every week, you're saving up for that retirement. Right, and we found that your future value would be $1,194,685.86. That was the first part of the question. Now it's saying 1 month after you retire. So right there, let's say that's month 1 after you retire. You're going to withdraw some amount. We don't know what that is. We'll call it X. If you wish to make equal monthly withdrawals for 25 years, so for 25 years after retiring, 25 times 12. That means you want to make 300 withdrawals. After retiring, how much can you withdraw? Well, what's happening here is you have a new timeline that's starting where the old one finished. So the future value of the first part of the timeline becomes the present value of the second part of your timeline. And now we're going to start getting into, the more complex timelines. A future value and a present value really depend on where the payments are. And so you see, when the payments were here and the future value is at the end of those payments, then we would call it a future value. But if I zoom into this portion of my timeline where this amount is at the beginning, well, this becomes the present value of this section of your timeline. And really the question is, if this is my present value, right? If this is how much I have saved up at the beginning of my retirement, well, what are my payments? How much can I withdraw every year? So now this becomes, first of all, an ordinary annuity because now the payments are taking place at the end of each period. And we're solving for the payment. So what do we do? Okay, let's go grab our formula first of all. Present value of an ordinary annuity. Again, I'm using the present value formula because that number, the 1.1 million, is now a present value. So I'm going to set that equal to the present value. The payment is what I'm looking for. 1 minus 1 plus, and now K. Always, even if you think you have it, double check. Do I have K? Well, let's go back and see. Well, I had K, except this was a weekly K. Now my payments are monthly. And I told you in the previous lesson that K and N have to have the same time frame. So I can't use a weekly rate if I have monthly payments. So we need to convert our effective weekly rate, which is the K we currently have, into an effective monthly rate. This has an F of 52. We want an F of 12. And so at the beginning of this lesson, we talked about the effective to effective formula. Well, here's another opportunity to use it. Okay, so the formula in question, if I go all the way back to find it, is this one here. So, have the habit of always at least asking yourself, do I have K? Or is this my K? Can I use it? So we're going to take 1 plus the old K, which was 0.001, I think 673, right? Yeah, 673 per week. To the power old F, 52, over new F, 12, minus 1. Okay, so 1.001673 to the power old F over new F, minus 1. Your new K, your monthly K is 0.0072699. And that's the K you're going to use here. And again, maybe I'm going a little bit overboard with these decimals, but when you start to deal with large numbers, the 5th and 6th decimal could make a difference. The N is 25 times 12, so we said that's 300. So negative 300 as your exponent, divided by 0.0072699. Okay? So we're going to be solving for the payment. Best way to do that is to punch this whole thing into your calculator and then just divide this by that. On your financial calculators, the 1,194,685.86 becomes your present value. 300 is your N. 0.72699 is your IY. Remember, that's this number times 100 to turn it into a percentage. 0 future value, compute the payment. So one way or the other, you get the same answer. So we had this as our future value, now it becomes our present value. 300N, 0.72699 IY, 0 future value, compute payment. You get about $9,800 and 84 cents. And you get the same thing if you do it this way. Let's prove it. I got exactly the same thing. Okay, so this is an example of a longer style retirement question, very common question on these exams. Okay, the final question of this lesson. You just borrowed $100,000 from JK Bank, and the bank has quoted a rate of 8% compounded monthly. So quoted you, that's APR. Compounded monthly, that's your M. You're going to repay with monthly payments, so your F is also 12. So again, this is a situation where you can do APR over M. So your 8% over 12 is 0.006 repeating. What is your monthly payment? Now, we're going to have a whole lesson on mortgages and installment loans, so this is just a kind of a preview of that. But basically, when you borrow money and you're going to make equal periodic repayments, this is just an ordinary annuity. In fact, it's very similar to the last step that we took in the previous question. Because the $100,000, the amount you're borrowing is your present value. You have your N, which is you're going to make payments for 10 years monthly, so your N is 120. Now you have your K, and we're looking for the payment. So it's exactly what we did before. We're going to take our present value of 100,000 equals the payment multiplied by 1 minus 1 plus K. So here again, if you can use a fraction, if that doesn't bother you too much, do it. Minus 120 over that. And you solve for your payment. So I'm going to start by punching this entire thing into my calculator. So I get a monthly payment of $1,213.28. Okay. So that's it for this lesson. Start to practice, right? You have a textbook online. You can find exercises on my website. But start practicing, get used to this, because in the next lesson, we're going to be getting into the more advanced timelines, which are growing annuities, growing perpetuities. We're going to introduce new variables. We're going to do mortgages, and then we'll get into bonds. We'll get into stocks, right? We'll get into the more complex situations where this is the base. If you're enjoying these lessons, once more, hit that subscribe button, and I will see you guys at the next lesson.